To the project and exercise lab. We can use the lab in South Hall, which has a 24 computer, but the problem is there is no whiteboard. It was asked to use the Word, but the Word sometimes it's not easy to erase. So let me have exercise lab in this room. Then in case I need like the handout, the car and the stuff, everything. So I want to announce in case if I feel the comfort to use the computer lab also, I will let you know, okay, through the message, okay, before class. At the time, in case we are using computer in the lab, the computer lab in South Shore, if you want, you can use your you can use your computer or you can use the PC in the lab. Okay. Anything else? Okay. Then the reading assignment, I'm not going to remind or check during the class. So it's already set the schedule on Canvas. Please follow the schedule. So you can submit the 1 or 2 pages summary of the given assigned paper. The first one is not required to submit it. It's just throughout the semester. It's an overview of deep learning because this is not course for the only deep learning. Instead, it's more like the data mining based on the machine learning. Okay, so we do not have enough time to cover each and every details of the deep learning, but some of you guys are very interested. So you can take a time to read and understand the overview of a deep learning paper, which is not easy for especially the master student who never did any the research or the technical writing, but it's a good experience to understand such a technical paper. It's the same thing for the undergraduate student. Okay, but from the reading assignment, that is the reading assignment 0. But from the 1, 2, 3, 4, we have a 4 reading assignment. None of them are easy to understand. So please take a time and read. I don't expect for all of you to understand and everything completely. Even I do not understand some part of such a paper. Okay, so take a time, try to understand as much as possible. So you can summarize based on your understanding, and that's the requirement of the reading assignment. Okay, do not copy and paste. So I'm going to use the Turnitin.com, so which will check the. So I know that you have friends who already took the same class before, just borrow their works, but it will be the copy. So the Turnitin keep all the previous submission record. Okay. So first time is a warning, but second time is a 0, and third time it will be the fail. Okay, so then today, I do not know what happened in this classroom. Probably the no class happened last week. So I can see my terrible note on whiteboard. But I'd like to continue my lecture for the mathematics. Okay, the basic of the mathematics. I know that some of you guys already understand everything, but it's time to remind what you guys learned during the calculus or the algebra 2, pre-calculus, and calculus. Is pretty much enough. If you never took the probability, also it is strongly required, suggested, to understand the basic of probability as well as the statistics. Okay, so I'm going to just introduce the very basic part of the probability statistics and linear algebra. But if you feel that you are very interested in the machine learning, AI, data mining, but do not have enough background in mathematics, please, this is also a good time to study the mathematics. So there are a lot of good material. The math for the deep learning, math for the not math engineering, math for the machine learning and so on. So you guys can find such the material So this is a presentation file I borrowed from the professor. This is a very the compact version. So you can find the full version or the somewhat description for better understanding. Okay. Let's continue. So last time we did the covariance and the correlation. So simply the covariation is the relation between the two attributes. Sometimes I'm using the name of an attribute, or sometimes the feature, sometimes the genre, sometimes the column. It's the same meaning. Okay. So data mining and machine learning use different terminology, but you guys can understand that it's a covariance show the relationship between two features and two elements in terms of vector, like that. But the covariance sometimes depending on the number of objects. If you have the huge number of objects, in other words, huge data, that increase even the covariance. So we can normalize, that is the correlation. Sometimes it's called the Pearson R. Okay, it's called the R value or the correlation. So it's the same meaning. It's basically normalized by the standard deviation, the variance of each feature. So covariance and the normalized. So that is a correlation. So we will see several times today and throughout the semester such a correlation and covariance. Even finding the correlation, the R, we can do some part of the data analysis or even machine learning. So we will see later. But here, if we have the positive value of the correlation, as I said, this is a normalized one. So which means the maximum value is 1 and minimum -1. So 0 means it's not related. Okay, so in case of 1, so simply the height and weight, the higher, the heavier. Okay, that is a positive. Okay, so positive relationship. So 1, so positive value. If not related, then it's a 0. Negative is relationship between number of hours, the Instagram, and your GPA. Right? The longer time you use the Instagram, the lower GPA. It's a negative. Okay? Negative values, negative relationship. So we can use such the correlation for data analysis a lot. So we will see today in more detail. Then jump to the probability. There are several rules you already know. Complement rule is for your reminder, it's the probability space. Okay? So actually this is not mathematics. Somebody said statistics is not the mathematics. But once we change the space into the mathematics number space, we can use a lot benefit of the math for the statistics. So that is called the random variable. So when we are using the omega means it's a number space? No, it's a statistics, the probability space. So it's the probability space. So something happened, event. So there are 3 things. So event. So something happened, not happen. So if a probability of not A, definitely is 1 minus 1 is the total. Okay? Total, the probability is the 1 always. Okay? So 1 minus P of A. So everybody know. So such a complement rule. Product rule is a little bit more complicated, but you can understand from such a Venn diagram. It's the same, the probability space. Then we have 2 events, event A, event B. Okay? So for it, we will see the example, like the white-haired person, white-haired man is event A, and the age over 65, event B. Okay, so in this case, the P of A, it's a white-haired person is the A, and the P of B is the white hair and over 65. Then I'd like to know the probability of the white hair, whether it's the over 65. At that time, it's the intersection of A and B. Then, at that time, we can calculate the P of probability of the A and B. That is, what is this one? It's a conditional probability. It's a base. So in case of B, what is the probability of A? So if this is 1/3 of it, it's a 1/3. Okay. However, that is not the probability of the P, A, and B because we don't know how much B, the P of B, event B. If nothing, in worst case, B never happened, probability 0. This one should be 0, right? So we need to consider the probability of B. So that determines the volume of the possibility of this one. This is a probability of A in case of B, but how much B? The probability B is. So this is called the product rule. So A and B is calculated by the conditional probability of A based on B. Why is it complicated? Because sometimes we cannot directly get the A and B. No way, sometimes. Instead, we can, this is kind of sampling among the B, so we know how many A, okay? So this is kind of from the real data, we can know this conditional probability easily. Then at that time, if we know the size of the B, probability of B, we can calculate this one, even though we do not know this, right? So that is the idea of the product rule. This product rule will create very well-known popular theorem. Anyone? The Bayesian theorem will be derived from this product. Keep in mind, so product rule is the P when we have the two events, A and B. Comma means A and B happen together. PA based on B. Yes. Times the P of B, that is a PA and B. We will use the so this is the product example of the product rule. So the meaning of this is among the age 65. So we know how many of them are white hair. We do not know how many white hair. Okay, so too many, but among the 65 we know. Then that is the 78%. Then we know from the entire group of population, the 65 is the 18%. Among the 80% is the 8%. Then we can calculate the white hair is over 65. That is this part. So we can multiply, that is the 14%. Okay, 0.14, which means even though we do not know this one, so we can calculate the probability of A, and B. Okay. Independence. So independence means not depend. Okay. For example, when I toss coin and dice, so we have two events. So rolling dice, the tossing the coin. Are they related or not? No matter what happens, for example, I can sequentially make the event. Toss the coin first. It's a head. Then what is the probability of the 1 from the rolling dice? So still 1/6. It doesn't affect each other. So it's an independent event. So in case of independence event, even though we calculate the conditional probability based on the coin, what is the probability of dice? It's still the dice, right? Doesn't affect. So that is the independence. Same thing, the P and A and B happen together. They are not related, but when I toss the same time and rolling a dice the same time, what is the probability of the head and odd number? You can separately calculate half and half multiply the P of A and the P of B. So then a quarter. will be the probability. It's the independence. Independence is also important in the data analytics. Which one is easier? The number one, the independence event. Number two, depend. Number one will be easier to calculate. However, in terms of data analytics, which one will be more effective? Related. If something, for example, A and B are related, I'd like to know about A, but it's very hard to get the data from A, but I know B. Then through the B, I can guess A. This is a way of the method of data analytics, data science, a lot used. It's the only correlation analysis you can find. If you can find, for example, so when I judge student, there are a lot of the factors. So he's nice and his personality good and so on. But my correlation regarding to the student is the GPA. I'm not sure whether that is correct or not. So through the GPA, it's a simple. It's just number. I don't have to consider this one, his personality, whether he is diligent or whatever. I don't want to check his schedule. But through the only if true, if GPA is related to the other feature of a person, student, then if I know the GPA, I can judge the student. I can decide whether I'm going to hire him or not. Okay? That's the kind of way of data analysis. Very simple way, but as you can see, so if really related is the 1, correlation value is 1, that's good. But in real case, it's not possible. Okay? Part of related and a lot variable. So that is independence. So example of independence. So this is a problem during the high school math, or if you, for example, participated in the competition math, okay, math Olympiad, math league, and the math count in US. So a lot of questions from the such event and probability. So first thing you need to clarify whether event. First you need to identify what kind of event. Okay? Then whether they are related or not, whether they are independence or dependence or not. In case of independence, it's quite easy. You can separately consider, like the rolling dice, the flipped coin, and the height to unrelated individual, like you and me. But in case of a twin, or in case of a father and son, or mother and daughter, so such a relationship, definitely DNA is inherited, it's related, right? So that is the dependence and so on. So you can clarify when you identify the event whether they are related, dependence or independence. This is other example in terms of random variable. It's the same thing, but we can use the random variable. So for example, the meaning of this one is in case of the y, value is 1. So for example, the y, in this case, y is who is the manufacturer. If manufacturer is European, in case of European, that means you only consider this part. So this is a basis. Then what is the probability of the x is SUV? Then you can count this, not the value of 0.05. Instead, the denominator will be this, and what is the probability of this one. However, if this one is independence, P of x is the same. Each of them is separate. Okay, so that is the independence and the dependence, and this is the example of in case of the random variable. If you are not clear what is the random variable, I think that most of you understand what is the probability and their space you learn in your early math. But the random variable is we'd like to assign, we'd like to make the probability as a function. Then we can use all the benefit of math operation and integral, whatever calculus. So to do that, we can use the variable for the event. Okay. Then finally, base rule. We have a time. I think I need to spend almost a day because base rule is also very important. But today, I'd like to very briefly introduce what is the base rule. Okay? Question? So tomorrow is a very important day for the UB. So UB will have the open house tomorrow. So that, however, the weather forecast predict tomorrow there will be rain. Okay? So unfortunately, so will be rain tomorrow. Then, but actually, when I checked the last year, so only 5 days a year was rain. Okay? Then, if weather forecast the predict the tomorrow is the rain, 90% correct. Okay? 90% correct is quite good. So that, what is the real probability of rain tomorrow? It's a simple question. So tomorrow is the predict the forecast, so it's a rain, but unfortunately. But when I checked the last year, only 5 days the rain. But when the weather forecast predict tomorrow is the rain, 90% correct. What is the real probability of rain chance tomorrow? Roughly 90%. Number one, over 90%. Number two, around 90%. Number three, less than 90%, but above the 20% or 30% in middle. But less than 20%, number four. What do you guess? Three. So between the 20 to 90, probably less than 90. Okay. Anyone else? Two. So 90%, because he always 90%. But there is a key part. 90% when the rain. Okay. He predict among the rainy day, he accurate 90%. Okay? Among the rainy days. But actually, if we calculate the real probability, it will be drop down to 11%. Why? It's a kind of an illusion. Okay? So first thing is, how many days rain really?
So
Only 5
so
out of 365. Even though 100% accurate, the 5 day among the 5 days he accurate 100%, but it's among the rainy day. But only chance 5 times. The other 360 days, it's not rain. Okay, the chance is actually small. What we want to do is we don't want to check how much he accurate. What we want to know is really rain or not tomorrow. Okay? That is much less than that. So that kind of thing is proved by Bayes 250 years ago, something like that. He was a priest, but he was interested a long time ago. A lot of priests and banker and such a people actually study the math a lot. Okay? Also tax, the government officer, they actually because they do not have a computer or even calculator. So mathematician actually did a lot of jobs such a thing. Then the Bayes was a priest and he was interested in the math and the statistics. He find the rule. So idea of the Bayes rule. I will show the math for to calculate why 11%. Not detailed today, but we have the idea of the Bayes rule is we try to find the relationship between the two events, not variable, not the feature value, it's the two events. At that time, what we want to know is the probability of B. Probability of what? The rain. Okay? Rain is our event. A is forecast. Okay? Because tomorrow the weather forecast say tomorrow will be rain. In that case, what is the chance of this one? To calculate this, the base find, so we can use the other information. Other information, that is the A, the probability of A based on B. What the mean is, in this example, so what is the probability of forecast correctly based when there is the rain? We know because we have the history. This is called the likelihood. So it's a very important term in the statistics, the likelihood. What is the meaning of likelihood? How much is similar? Likelihood, okay, likelihood. Then, in terms of statistics, one of the problem of the probability is, as in case of district, we know the probability of 1, probability of 2, 3, 4. However, in case of continuous case, okay, continuous, if I try to know this is the height, okay, 5 feet, the 2 inches. What is the probability? We cannot find. It's actually 0. Because it's a continuous. There is no volume of that. That's the problem. So to address the problem in statistics, we need to construct PDF. You heard about the PDF? I'm very weak to memorize acronym. PDF and CDF. CDF commutative, and PDF is probability density function. Density function. Okay, we need to consider this one. Okay, then why did I mention this? Base rule. Oh yes, likelihood. So to know about the likelihood is very similar as the probability. So probability is we make the event, then we can calculate the probability. We try to know this kind of thing, sometimes the distribution, or the bad shape the distribution, normal distribution, or some Kai's the distribution, or something, the Poisson distribution like that. From the event, the probability. Likelihood is kind of opposite. So we try to something happen, okay, but we do not know. We try to know something, the characteristic of the event. So that is how much similar to this one or the Poisson like that. Okay. In other words, in case of Gaussian, it has an average and the variance. So how much fit to this one? How much fit to this one? We try to keep the kind of experience or characteristic of the event from the sample. Okay, from the sample. So when we do something like the forecast rain or not, that fit to let's say this one, how much similar? Okay. In terms of probability, that is how many chance of correctly the forecast predict. Okay. So this is the P of A or B. How can you get? It's the likelihood of the probability is called. So likelihood will be used a lot later. But nowadays, it's yes, still used. Like the maximum likelihood, MLE, or log likelihood, there's something there. Okay. But the MLE is more popular. So then go back to here, this is such a likelihood. Okay? We understand the characteristic or how much accurate of that weather forecast like that. Okay? Then This is a P of B and the P of A. We can get the P of A, how many times the rain, and there the accurate, how much accurate of the weather forecaster, right? So this one is called the post, and it's the prior. So by combining this one, we can calculate the posterior, the probability. We will see more details. We will prove. Proof is very simple actually. We can use this one. And B is P, B, A, the P, A. Because it's the same thing, right? Then the P, the B, A equal, we can go to here, P of A, P, A, bar B, and P, B. So already proved. So this is really simple, but this is really powerful. So I cannot remember exactly, even I do not know how, but 1980 something, the submarine, the USSR, the Soviet Union submarine, or the submarine was sunk in the ocean. Then at the time, the military, they found sunk the submarine using Bayesian theory. I don't know how, but they did. So this is the base rule. So at the time, this is a posterior priority post. We'd like to know this one based on what? Likelihood is kind of characteristic property of the A in case of B. So then the P of B, P of A, we know. So then we can calculate that. For example, this is the example of this one. So P of B, we already know how many days, rainy days a year, and how A based on B, the 90% accurate in case of rain, right? So it's a 0.9. Then, by applying to directly the base rule, so this one, so we know this, okay, and we know this P of B, 0.9, 0.00137, and the P of A is a product rule that we have seen before. So this plus this, meaning is the P of A bar B is for the P of B and the not B. In case of B, what is a B? It's a rain case. We have not rain case. Not rain case and not B, so we can calculate. Then the final, the probability is 11%, which means you can do it's around 1/10, so you can do the open house or the night. Okay, we will see more details. The base rule, the later. The classification. Nowadays, we can use the base as one important method of the classification problem. So decision, when we decide something, okay, then keep going the probability, add, multiply. So I think Then the next one is linear algebra. Go back to the linear algebra. So linear algebra, we can build the equation, especially linear equation. Linear equation is, what is the degree? It's 1. But if we have the one feature value, one variable, we can build the AX plus B. Okay? If we have a multivariate problem, we can have AX1 plus A1x1 plus A2B, X2, A3, X3 plus the B, like that. We can build a linear the equation for the problem, which is called the model. When we build such a model, the next thing is optimize. Optimize means best solution. We can find the best coefficient variable, then solve the problem. So that is the linear algebra. So linear algebra can be used for the vector and the matrix. And also transform. When we transform, we will see some of the example later. When we transform, we can use the linear algebra. And also dimensionality reduction, I will introduce. So then the PCA, is one of the example to how to reduce the dimension. Definitely, which one is easier to process, to analyze? The huge dimension or only one or two dimension? In other words, huge feature characteristic of him or the only one or two feature. One or two is easier to decide whether he is a good guy or a bad guy, right? Well, he is a good student or a bad student. Only GPA, but he has characteristic, how much kind, or his account, and all other information. Some of them are good, some of them are bad, so it's very hard to decide. It's the same problem in the data analytics, data mining. So sometimes we'd better reduce such a dimensionality, then we can solve the problem. So to reduce the dimension, even we can use correlation. If a lot of features are correlated, we don't have to use all of this, right? Only one of them. That is one way to reduce the dimension. However, nowadays, this dimensionality reduction, we don't care sometimes, like the deep learning. So even we consider each and every case, okay? Like when we collect the information through the five senses, vision, the hearing, or the sometimes touch, all the information, our brain, so receive the process huge different the feature, very high dimension. Then it's a process finally decide he is a good student, okay, or he is a bad student, like that. At that time, we are not sure whether the brain has such a process dimensional reduction, but people still believe we collect all the more information, the better to understand him, okay, to judge him, right? So at the time, so we couldn't use such a process before because it's a huge computation. But nowadays, with the power of the computer and the algorithm like the TensorFlow like that, we can process. So without reduce the dimension. Okay? Extreme case is the images. Image, for example, 800 by 600 resolution. Meaning is it has how many? 800 pixel. So 600 pixel. Pixel means this one, the bird. There's one bird. If this one is the color, okay, RGB, red, green, and blue. There are three. The LED, for example, okay, red, green, and blue. So each one has the 3 times. Each one has 1 byte. Actually, 256 different color, but it can be 2 to the power of 8, right? So 8 bit is 1 byte. So 1 byte. So how many different? 48,0,0,0,0 times 3. Let's say this one 1.5 mega number. So each of them is the one feature. Then we can process it. Convolutional neural network use such an entire image as the feature input. Very high dimension, but still it works. So keep in mind. But conventional way, the traditional, the data analysis, they use the dimensional reduction. Linear regression, today we are going to take a look at the regression also. I think that in the high school math, you already know about the example of the linear regression. For example, we will see later, but for your quick understanding, this is the height and this is the weight. Okay, so 4, 5, 6, 7, and the weight 100, the 110, like that. So we can plug this. Okay, then can I say that this is like this? Pretty much. So if we have person 5 feet 10 inch, you can guess what is the weight. So 120 pounds, like that. At the time, this is called the regression model. So we can decide such a regression model. Regression model actually show the relationship between two variables. Different from the other correlation and covariance is that at the time this variable is called independence variable. Independence. Then this one is depend on input. So dependence and independence variable, their relationship, if we model through the equation, linear equation, that is called the linear regression. We will see some very briefly about the linear regression also. And also you have used such a linear system with linear algebra, okay, and many other. Okay, so first the vector. Most of the data represented by the such a tablet style, the column and the rows. Okay, think about the database design class. Database design, we call this one instead of the matrix, we call this as table relation. Okay, relation. So relation consists of what? Number of attributes. Similarly, this one is called attribute, or sometimes called the genre, sometimes called the this one is called attribute, or sometimes called the column, sometimes called the genre, and sometimes it's called the attribute, column, genre. I forgot the one. Feature. Feature. They are the same meaning. Okay? Data mining use the feature or attribute, and the machine learning and data mining, but the database use column or attribute. Okay, that is then if we combine as a group of such an element, that is called the vector. So if we build a vector for the feature, that is called the feature vector. So when you take a look at the code for the many data analytics, you will see something F, or the F related thing. That is a feature vector, or the feature, like the F of V or the F underscore V is a feature vector. So mostly in Python, it is the array, the list. There is no array in Python. Okay, most similar thing is the list. Or nowadays we are using the dictionary. Dictionary has a key, okay, and value, but a list has like the array. In case of immutable, it's a tuple. Okay, so then by combining all feature vector, like the one feature, one vector, another vector, then combining this is called the matrix. So matrix is the n by n. N is the column, n is row. N is usually represent the data item. And each data has the n number of feature, n number of the attribute, like this. This is the matrix or two-dimensional array. So first one is A11 through the A, M, N. However, don't be confused with the Python programming. As you know, our computer science index starts with what? Always 0. So in computer programming, it's a 0. Index is a 0, 0. Okay? This one is a n-1, n-1. Always confused. Okay? Especially when you are using Python, it's a range. Okay? So that is a 0 to less than the value. Range 5 means 0 to 4, like that. If you do not know what I'm saying, study the Python. It's 1 hour, 2 hour the exercise. Okay. So this is a vector and this is a matrix. Oh, one more variable also. Variable is also different name. Okay. Then the vector. So what is a vector? Anyone who can explain what is a vector? Coordinate. That's good example of the vector. So what kind of coordinate did you use before? Well, X and Y coordinate. It's a Gaussian space. Gauss is a very popular, famous the mathematician. He used the space to coordinate two variables, X and Y coordinate, and show. What about I have another one, Z. The Gaussian space is not good enough. We need to extend another one. So X and Y is good for our the math, high school math. Y equal f of x. So two variables, X and Y axis like that. What if one more? That may be possible. So C is f, x, and y like that. How? We can draw another perpendicular axis, the Z, like that. What about the one more? So this is the very limited small example of the coordinate if we are using the coordinate for the element of a vector. Yes, do, but generalize. As we have seen, our feature set, feature vector is the 100,000 million. Okay? Sometimes we call this, if we imagine such a space as a hyperplane. So we can imagine, but it's imaginary, very hard to understand. So to generalize such a x and y is the kind of feature. We can use the real number for x, real number for y. That's one very limited example. But our variable is not only such a number, but it can be age, it can be characteristic, it can be category. It's a bunch of things. How can we represent such a thing? At that time, generalize such a the feature set as the vector. So vector has a group of what? Element. Actually, definition of vector is a set of element, group of elements. E1 and E2, E3, En, number of elements. This is a vector. Then vector can be represented by such a form or this transpose. So if you see the T, okay, a lot of time we can the X or the X of T transpose because later we will see multiplication should match the column and row. So we will see this. So this is not good. You can understand. So actually this is an example of the vector two-dimensional space. Like this, add is like this, and so on. And this is a three-dimensional example. If you can open your lecture notes, you can see that clearly. But this is not a good example. Let's move to the next one. So there are several characteristics of the vector. So we can add. We can do the operation for the vector. In case of addition, is addition of two vector is an element by corresponding element can be added. Okay, x1, y1, xn, yn. The illustration of the so we can understand the vector limitedly in geometry space because in geometry it's intuitively easy to understand. Okay, not always is possible. Right? If you are using element for the filling or something category. Like the grade, we cannot just the illustrate using the geometry space, but it is doable. Multiplication scalar scale, so we can extend or shrink the magnitude, which is called the magnitude. Vector illustrate the direction, but to know the more detail, we can calculate the magnitude. Magnitude is the size of the vector. Dot product is the corresponding the element will be the multiplied, then the adder. This is a sigma, everybody knows. It's a I is the element, the index of the element 1 through n, the sum of this one, which means output of such a dot product is a scalar, not vector. However, the other, the addition and scalar multiplication output are the vector also. So that product can be illustrated by in geometry space. It's like the multiply and the x and y magnitude and their cosine the value. Okay. Which means if the perpendicular is the highest value, otherwise if the low is less than the perpendicular, that is the dot product. Then the matrix is kind of the generalization. The vector is a generalization of the feature space, and then also the matrix is a generalization of the vector. So we have n row and n column. To clarify, n row, n column. Not important, but clarify. Okay, so we have A11 through the AMN. M is indicate the number of rows, number of data, and this one is the number of columns. So from now on, whenever you see the programming two-dimensional variable, so this one is always the data. Okay, this one is the attribute. Okay. There are several the operation in matrix. The transpose is change it, swap the row and column like this. Okay. I think you guys already know that I can quickly move up. So addition of the matrix, we can add the corresponding. Definitely it does support. I forgot the name of the rule suddenly. We will see. Probably. So and the scalar multiplication, we can multiply each element by the scalar. So scale. Oh yeah. So associative rule, commutative rule, and transpose rule. Transpose is the row and column switch. At that time, the order will be changing. Oh, by the way, commutative is not the generally. Okay. There are more at the matrix, but the most important part is when you multiply the matrix A and B, the number of columns should be the same equivalent to the number of the rows of the B. Okay, this is the most important part. I think that everybody knows this. So in this case, A times B is doable. Okay, then output is 3 times 5, like that. Okay, then the vector projection. So this one is called the norm. Okay, this is the magnitude of the vector. And the projection means is the perpendicular, the lag, then the multiply the scalar of the cosine value of the y magnitude. This is the vector projection. Okay, so that is a quick review of the linear algebra and the probability. Then the next thing is once, for example, if we have the problem, like for example, height and the weight problem. Is there any way to guess, predict the weight for a given height? So I know that his height, but can I guess? Can I predict his weight using something? So one of the solution is if we can find such a regression, okay, linear equation. Then using this one, the input and output we can check. The problem of this is how can we find this? This is called a model. Specifically in this case, it's a regression model. If we are using any other model, it's okay. Model is a standardized. It's a standard. Standard between the two variables, especially input, the independent variable, and output, the dependent variable. We find any model that lead to this kind of the data. Okay? It's not possible to build a model that 100%. It's an ideal case, which is not possible. The real data will be away from such a model. Then our goal is what? Minimize such an error, total error. Okay, our goal is to build a standard. Actually, mathematically, our goal is to minimize such an error. This error is called the margin. So sum of margin is minimized. At that time, how can you represent this margin? Difference. Okay, 1, minus 1, 1. But minus 1 is still should be 1. So to keep the absolute value of that, we can do the such a error margin. However, if we wanna, for example, here, if we have this kind of the prediction, it's a huge error. So we do better exaggerate the such error, and also if this one is very close to this, almost the touch of the model, we try to ignore such a thing. At that time, we can square. If we are using the square of the error, what's the benefit? We don't have to absolute, and also the bigger error will be exaggerated. So we do not use such a thing. But the nearby, we ignore such error, so it's closer, easy to build such a thing. So this one is called the mean squared error. If we average or the squared error. So it's most of case we use such a quadratic equation. What about the cubic? Why not using the power 3? Minus will be minus. What about 4? We can exaggerate and we can ignore this one, the extreme. This one may have later local minimum. What we want to do is minimize such an error, okay, which is called gradient. This is a gradient, and this is, if we can find this point, that is the reason when you are doing the algebra long time before in your middle school and high school algebra, introduction algebra, you find this value always. Do you remember that? So does the math teacher explain why you need to find this one? This is the most important part of this quadratic equation. Example is this error, squared error. Okay, our goal is to find this one. How can you find? Derivative and equals 0. If you derivate equals 0, this one. But from the experiment, you can start from here and getting close to this one until it's not changing. This is called the gradient descendant algorithm. The gradient descendant algorithm is the main part of deep learning later. So this is called optimization. The gradient descent algorithm is one of the example. Optimization means we try to build optimized model. Okay, that is one example in the regression model. But many other models from now on in this semester, we actually focus on such an optimization. Okay, then the maximum likelihood is from the, as I explained before, likelihood. So it's the probability distribution. If we assume our data is formed such a Gaussian distribution, for example, our goal is to find such a parameter value. How can we find the parameter value? How can we build a model? So same thing. So we try to build a model, standard model. How can we find? At that time, we can use the maximum likelihood. Okay? We will see the sum of the example later. And another example is expectation and maximization. It's an iterative model. So we will see later pretty much when we are doing the clustering for the expectation maximization, maximum likelihood during the naive Bayesian model. So it's during the classification. We will see later. Gradient descent algorithm is discussed during the deep learning. Okay? So that is optimization. Here. second part is a continuing such a probability and the linear algebra, more specifically. So, if we build a model for the same data, okay, so this is the conventional way, traditional way to analyze the data. I have a sample data for the grade, the exam score. So exam score. So, but I cannot collect the all exam score for the entire university. So I have some of them. So I found this and this and this and this. So this is 30, 40, 50, 60, 70, 80. Okay. And I guess this is like the distribution. This is called the Gaussian distribution. So if I can model such a problem as a statistical model, okay, statistical distribution, then what we want to know is the Gaussian distribution can be represented by what? Average, mu, and it's a variance. So if I know the two parameters of the mu and the variance, actually I can model entire one. Even though I do not know exact value of this all the cases, but I can model. So at that time we can optimize. Then finally we can model the problem using Gaussian distribution. Then if new data coming like the 55, how many percent? So we can apply it. So at that time we can use such a statistical distribution. Especially Gaussian, there are many different distribution, but 99% case in the data mining and the machine learning, we are using Gaussian distribution. So why Gaussian distribution? So Gaussian distribution is similar as what? Normal distribution. What is the difference? Normal distribution and Gaussian distribution. Anyone who never heard about the normal distribution? Everybody know, right? Most popular and introduced in the math textbook, there's a normal distribution. By the way, if you translate the normal distribution, normal, into Korean, which is my first name. Really. So my name appeared a lot in math textbook. Really. But however, meaning of my first name is not standard. It's a different meaning, but it's the same pronunciation. But so normal distribution, as the name implies, normal. What about the Gaussian? They are same, except if you use mean value, average value into 0. So you can shift this one to the minus 30, minus 20, minus 10, 0. Highest value, mean value, average value into 0, that's normal distribution. So normal and Gaussian, exactly same. Only difference, average shift. Okay. Then, that's not very important. Instead, why we are using Gaussian and the normal distribution a lot? That's the main question. Why? 99% when you read any paper, textbook regarding to the data analytics or the data mining or the such a thing, they are using Gaussian distribution or normal distribution. Why? And even this Gaussian is the first distribution in this slide. Then why? That's the most important question. No? Because it's normal. Anything. There is if you think about this one is the exam score. Exam score. So if you make the distribution with the real event like the midterm, final, it's like the this. Average, a lot of students, 60, 70. In case 50, 60 is on average, I usually apply the curve to make the 60, 70. That's a shift. But before or after shift, it's like the 100, few students. 30 square is a few students, mostly in the middle. That's very intuitive, natural. Any kind of event, think about. Sometimes, some of the event like this one. Something happen here, then, and this. It's called the Poisson distribution. However, if we repeat such the event again and again, it will be, on average, if we make the several times, usually more than 15 times, any kind of the event, no matter what types of distribution it has, it will be moved to the eventually normal distribution or Gaussian distribution. This is called the central limit theorem. So central limit theorem is the most important theorem in the statistics for data analytics. I'm not going to explain the details. This was the final exact question to prove during my PhD, which I couldn't answer correctly. But I took the core course of the statistics major, so during my PhD, but almost failed. It's really hard. I didn't learn anything. It's like the writing a paper. It's like the English essay. Answer all the questions. It's really tough. But central limit theorem shows that any kind of event, it's intuitively. Think about if something happens again and again, there might be middle, right? And rarely happen. So that is the idea of the normal distribution. So because of that, normal or the Gaussian distribution is used a lot. Another reason is it can be represented by mean value and their variance. Mean means where is the middle? Like this. This is the mean. In Greek, letter is called the mu. And the sigma variance is the y. How much spread out the data from the middle. So it's determine the shape. Bell shape, sometimes we call the Gaussian as a bell shape. So this bell sometimes thick, sometimes narrow. So depending on what? The variance. So what we need is for the normal distribution or Gaussian distribution, the normal is 0 and Gaussian is the only 2 parameters. We need only 2 parameters. In other words, if we guess 2 parameter value, in case normal, if we can guess, predict, find this one, the variance, game is done, game is over, right? We can predict any kind of thing. So this is the reason. This is called the parameter. So from the distribution point of view, optimization problem is called whether we can find the parameter value. How can we find the parameter value? At the time we can use maximum likelihood ML. Maximum likelihood, the event, not event, expectation. Maximum likelihood, the expectation. Something weird, but like that. So MLE can be used. So that is the Gaussian distribution. So two key parts, mu and the variance. In terms of mathematical equation, it's you don't have to memorize this, but at least you can understand. So this is what? Constant. Any variable is a constant. There is a kind of coefficient that determines the volume of this one is going to be the 1. It makes the 1. Then this one is a shift. Determine the mu. Okay. Then this one determine the spread out. So this is a Gaussian distribution. different Gaussian distribution. What if we have the multiple feature? So this one, only one feature, okay, inside. One feature, like the square, or even the not two. It's only one feature, one variable, one the characteristic. What if multiple feature, multiple characteristic? That's called the multivariate Gaussian distribution. In the there's a, I think that we have the figure to show the multivariate. Not here. If we draw the, it's like that. Okay, there are two bounds, or the two variable, or the three, like that. So this is a multivariate, the Gaussian distribution. We need to find the mu1, mu2, mu3, sigma 1, sigma 2, sigma 3 in the multivariate. So in terms of equation, it's like the, you can see the what is this vector, because we have a multiple feature. So we can use the vector. Then what about the mu? Mu is the vector. Mu1, mu2, mu3. And what about this one? Sigma, we have how many sigma? Sigma 1, sigma 2, sigma 3. But also variance related to each other. For example, in two variables, so they related to here. In case of 3, where's the 3? In case of 3, so related, they related to each other. Because if you draw the normal distribution like this, they are related to each other. So to represent such a relation between the variable, we can use the covariance matrix. In other words, we can have the sigma 1, sigma 2, sigma 3, and sigma 1, sigma 2, sigma 3. So then make the matrix how much related using covariance between, they are the same, so 1, 1, 1, and the related covariance value, we can create the covariance matrix. Okay? So this is the, in case of a 3 variable, 3 by 3. In case of D, it's a D by D covariance matrix. We already so what is a covariance? It's not related, it's related to each other. Almost. Okay. So this is a two-dimension, x and x1, x2. So we have the two, I think that in this case is a normal, so 0 and 0. And this is the variance between even sigma 1 and sigma 1, they are covariance metric. We can see the sum, that's that, the distortion like this. Because of that, this is a 0.25. If this one is like that, it should be 1. Okay. So this is a multivariate vector projection we did. Then I already explained if we can model the problem with a linear equation, this is called the linear model. Linear model is the maximum degree is 1. So for example, if we have the d-dimensional the variable like the vector x1 through the xd, so we have the beta 1, the beta 2, beta d, like that. In general, we can say the alpha plus the beta times x. In this case, the beta is our model. X is the independent variable, the input data, and the C is the predicted data. At that time, we can call the vector is our model. In overall, this is called the linear model. Example is a linear regression, like that. Okay, then one more thing. We can use the output of this one directly for the linear. That is called the linear regression. However, if we measure the output like that, sometimes if we have the extremely big one, this model doesn't look like good. Or sometimes, what if we are going to use the linear model for prediction? This is yes, this is no. So if the value is like the positive margin, we can say this one is yes, this one is no. And this one, really yes. So to clarify, the yes is 1, no is 0, like that. So we try to output of this error function, like this, output of this one is the 2, actually error is y minus y hat and square. Okay, so original value and the predicted value, there the margin is square, either is the power. Okay, this is the squared error. At the time, our goal is to use such a model as a prediction classification problem. However, if we use directly, this one sometimes a really big number, minus number, so we try to map the output of the model as the 0 to 1. It's not like this. So at that time, this is called logistic function. It's called the activate function to activate our classification. Then we are going to use this is 0.5 logistic function. Actually, this function is 1 plus e minus x 1 over this one. You have seen this kind of function in the calculus class. So bigger and bigger, it will be maximum 1. And the minus is 0. So which means if the value is less than 0.5, that is the 0. It's a no. And bigger than 0.5 is 1. Yes. So we can use such a model, linear model, for the classification part. So later, we will see this kind of activation function during the neural network. Okay? When we are using the neural network for the classification, we will discuss more detail. Okay? So this is the linear model and their activation function. One of the examples is we can use the logistic function or the activation function. I'm going to quickly move, but the idea of this one is to understand such a linear model from the geometry. In geometry, simply, like the linear regression, our goal is to find the line, right? How can you find the line? Two variables. One is slope, okay? Another one is intercept, okay? So which one is more difficult? And also important? Slope is more important. This kind of intercept is just you can move up and down and find this side. But this is a kind of rotation. So that is called the W. So W represents the model. Okay? Then the intercept is kind of bias. Okay? So shift is a bias. So then if we have the certain input data, then decide whether this margin is the positive or negative, or the yes or no, or if you are using the activation function like the logistic function, it's 1 or 0, like that. Then we can use such a linear model for the yes or no. The reason why I'm saying the yes or no, I'm using the yes or no is based on hypothesis. So you build a hypothesis. If the height is bigger than not bigger. If the score, midterm score is bigger than 90, it's the A, something like that. It's a hypothesis. Then the proof, yes and no, something like that. Then we are going to calculate the margin per tip or the 1 or 0. Then we can use the classification. Logistic regression is one of the linear model to classify. Okay. I really speed up to finish the math, the background, the review of the mathematics. Then after a short break, we are going to continue the pre-processing with the PCA and the regression. I introduced already a little bit, so we can quickly go on. Then I will introduce the PCA. Okay. 10-minute break. Yes. Manipulate the data for better result. So which means data itself can affect your data analytics result. So which means when I use their data, okay, introduced in the paper, it works. But when I apply my data for the same problem, same exactly the same approach, same parameter, but output is much less than, accuracy of the output is much less than what the paper said. So accuracy of the data itself is important, also completeness, okay, and consistency. So consistency, even though we take a part, so which means the part of data applied should work like that, okay, and so on. This one is an interesting part, interpretability. This is important in data mining. Data mining would like to use something result to understand the knowledge of a pattern, whether we can understand the result or not. But nowadays, it's a really high dimensional data, and also it's a huge amount of big data, so it's very hard to interpret. Even sometimes the deep learning or the neural network is a hidden black box like that. So we cannot understand, even though we cannot interpret the meaning of that, just the result. Yes or no. Then we apply. We don't know how, why, something like that. So interpretability is the issue nowadays for the deep learning. Okay. And there are several tasks during the pre-processing. So you can intuitively understand what are they. So like data cleaning, we need to clean the value. There are a lot of missing data, like for example, this one. This is an example of the LinkedIn data. When you download the LinkedIn data, a lot of missing part. Okay, really a lot of missing parts. So it's if we apply the data mining algorithm, machine learning algorithm, output is not that good because of such a missing data. Okay? Or that is the problem of the data. So we need to clean up such a data, and sometimes we need to integrate the different source of the data. So I'd like to analyze the traffic, the climate, information climate, the data set coming from the NOVA, or sometimes it's from the source of the forecast. So you need to combine the different set of the data. They are using different name of attribute, different scale, and so you need to combine, integrate such a different dimension and the data compression and so on. Okay? So this is actually the step of the data pre-processing step. So this is a cleaning and the integration and the transformation and the reduction. We will focus on the data, the reduction part later. Okay. First, cleaning. Any incomplete and also noise and inconsistent data we'd like to change. The problem is how. So we can use the brute force way is the manual. But when you have the 100,000, maybe possible, but when you have the millions of data, 10 millions, billions of data, it doesn't make sense. To the cleanup such as incomplete data or the fill of the missing data manually. So we need to apply some technique at that time. So we can use some the rule one way is we can apply the rule. Not always the rule is possible. Sometimes we can apply the mean value, but sometimes the unknown value. Because of that, a lot of times you can see the unknown data, which means it's missing data. But if you do not have the, if you do not fill up replace such a missing data, the average or the output will be distorted. So we can put such unknown, but the average can be used. Okay. And sometimes we have the noise data. Noise data is unexpected data. So in case of unexpected data, we can address like the smoothing. If you have the outlier data, like this is the normal data, but sometimes you have such the outlier data, we can smooth such a data. Then this one will be reduced like that. So we can use such a smoothing technique, or the data we can another approach is the binning. Binning is the box, so we can grouping. Or we can use the regression model. So like by applying the standard model, so such outlier will be removed like that. So this one shows how to address how to handle the noise data is using the bin. Like this, for example, grouping. So after we sort the data, like the group by 3, then for each group, sometimes we can smooth by the average value, or the smooth by the boundary. Boundary means the first one is a 4 and the nearby 4, and this one is 21 and 21 and 25, like that. Okay. Clustering is the grouping. So like by grouping, so this outlier will be removed like that. We will see more details during the clustering, the analysis. What is the clustering itself? Okay. Integration is another issue during the pre-processing, like the different source of data. The one typical example is the different name of the attribute. So that is one issue, and but nowadays there are even the tool. So to find the same or the similar feature based on the data, not based on the name of an attribute, but based on the data. And redundancy, I'm going to quickly move. And also, if you can find any correlated data, using the correlation, we can fill up the missing or the noise data, like that. At that time, we can use any correlation analysis technique. This is one example, chi-square, which we do not use a lot. So I'm going to skip this part. Chi-square, we are going to skip. Instead, we are using, you remember that this is the correlation, correlation variable Pearson R value, which is the normalized covariance. It's the same. It's a different notation, but it's actually the same thing. So this is the variance, and this is the covariance between the two, the A and B, and this is the variance and the normalized by the variance. It's the same thing. It's a Pearson R value. And the positive is a positive correlated negative. So using the correlation analysis, we can pre-process the data, which means we can guess the missing data, we can remove the noise data, and so on. This is a correlation and covariance. Data reduction. Data reduction is there are two types of data reduction. The one is the reduce the dimension. If we have the huge number of attributes, it's not easy to process. So we can remove the such an attribute. Then question is, what kind of attribute will be removed? Important or non-important? Definitely non-important. What is the non-important? In other words, what is the important variable? That's the question. So let me give the one example. We have such a data. This is a feature A, this is a feature B. So whatever the values here, so we like this and the plot. So in this case, which feature A or B, which feature is more important? Why?
Because regardless of what value A, B is always about the same.
Which means variance A is spread out. Okay, it's easy to identify their characteristic. This one is low, it's a medium, it's a middle, this is a high, like that, for example. Or this is the A and A1, this is A2, A3. We can easily classify, we can easily understand. However, from the B, if we project the data to the B, it's very narrow. So it's very hard to differentiate. So in terms of data analytics, the A, feature A is more important than B. In other words, what is the good feature? Higher variance and lower variance. High is a better feature. So when you remove the feature, remove the attribute, which one will be removed? High variance or the low variance feature? This one is not important, right? We can take out. So when you reduce the dimension or during the data reduction, if you want to remove the attribute, you can remove non-important attribute. Is not the low correlation, okay? Low and no low the variance data. And also, when you have correlated data, highly correlated data, do you want to keep both of them? If they are identical, we don't have to keep both of them, right? We can take, like for example, tax and income. They are highly correlated. So when you decide the credit, income and tax is almost the same meaning. We don't have to keep both of them. Instead, we can keep one of them, like the income. Okay, so that is the data reduction in terms of dimension. What about data? So feature, we can reduce number of dimension or number of feature. But when we have very large data, nowadays it's not a big deal, but sometimes the huge amount of data is struggling. We're struggling from the size of data. So we can reduce the data, number of data items. There are different ways. One is compression. So long time ago, when you purchased a PC, personal computer, there are interface slot, like the motherboard, and like the graphic card, and so on. It's called the ISA slot. Nowadays is a PCI slot, right? But a long time it's an ISA slot is longer, the slot. Then one of them is used for MPEG slot, which means when I display the MPEG video, CPU itself is not be fast enough. So all MPEG file go through the device, then uncompress and display. So then even the display is a display card. The VGA card will be used for the better quality of the video, like that. Which means when we have the computational limitation to process the data because of size or amount of that, one solution is compression. So compression, even the data analytics used the compression technique long time before, but nowadays it's not a big deal. Why? Hardware itself is fast and good enough to process entire big amount of data. It was a problem to process huge matrix like this one, like for example, 10,000 feature and 1 million of data is a huge matrix. So people would like to use graphic card. It's called the GPU. So GPU actually for the graphic card. So graphic. But graphic is the n by n, the pixel, almost identical. So this processing is used for this matrix. Then this one is called the tensor. So we have the specialized, the library to process this one is a TensorFlow. A lot of our data can be represented by such a big matrix tensor, so we can get the benefit of this. Do I have to use the TensorFlow? No, you don't have to. Even you can use the CPU without the GPU, and you can use the array, but it takes much longer time. It's not optimized. That is the reason as a back end, we can use the TensorFlow with the GPU for faster processing. Then the data analytics library provide the specific the package for TensorFlow and this one. So when you install the TensorFlow, you need to specify either GPU or CPU. If you have anyone who have the GPU on your laptop, anyone? So you can install the TensorFlow GPU. If you do not have, or if you are not sure, you can install the CPU. GPU is definitely much faster. Okay. Nowadays, most of the machine learning use such the GPU, but our practice is small, based on the CPU. So if you do not have, or if we are not sure whether you have the GPU, you can still install the CPU version TensorFlow. Okay, so that is the data reduction. So we do not use a lot of this, but you can see the regression is also the data model, data analytics model, and log linear is a logistic, like applying the logistic, the activation function, which is a very important concept later during the deep learning, and also histogram, clustering, sampling. All of these are very important, the concept and the algorithm in data analytics. But they have used the data reduction algorithm, but this is a small example. So throughout the semester, including today, I'd like to introduce the regression and the PCA, and also later we will see the details of this one. We are not going to use this technique, but this is also important in not only the data reduction, but image processing and the signal processing and many of the engineering area, which is called the Fourier transform. Anyone who took the signal processing class in E, you learned the Fourier transform. So question is, what is the Fourier transform? Can you share your experience? You cannot remember. So Fourier is the name of mathematician long time before in French. French? I hope so. It's a French. It's the 18th century, the Fourier. So he found very important the algorithm is the Fourier transform. Simply, have you ever seen this kind of thing? It's kind of a echocardiogram, like the signal. So this kind of the signal is called the periodic graph. Okay, so there is a period, repeated. So Fourier transform means any periodic curve can be replaced by combination of sine and cosine form. Okay, so this one can be represented by the sine and cosine. Then what is the benefit? If you can represent any curve using the sine and cosine, you can change this space is a time and magnitude. But we can change this one into the frequency domain. This is a special domain along the time, okay? But this one is not special domain, it's a frequency domain. Idea is, there are certain bands happen a lot. This one happen a lot, and this one is less. For example, if the noise signal interfere this, like this is noise. Noise is also periodic signal, then it can be added, distort, like this. I'd like to clean up this signal. How? Do you need to check each and every one? No, it is almost impossible. Instead, if you transform this one into the frequency domain using Fourier transform, it will be represented as this, like the frequency band. So this one represents this high pitch, and this one represents low pitch like that. This one represents noise signal. Because noise is also curve. Curve can be represented by the sine and cosine form. Then that show the specific band. If we take out this, just cut, and take out this one, like that. This is a frequency, clean the frequency domain. Then another beauty of the Fourier transform is this one is inverse. Always inverse is exist. We can go back to the original signal without specific band by removing this. So this is the idea of the Fourier transform. Very similar? No? Not much? So this is a Fourier transform. Meaning is, if we have a lot of data, like this, unlimited, infinity signal, but if we transform into the frequency domain, it's like this. This one is used for everyday you use, at least every day. JPEG. What is a JPEG? Image file. Actually, JPEG is from compression technique. It's a compression. MPEG. MPEG means it's a what? It's a compression for moving picture group. They propose the standard of the compression for the video. It's an MPEG, MPEG 1, MPEG 2, MPEG 3. For example, MPEG 1, the video has audio also, sound and the visual information. Sound is using specific layer. It's a layer 3. So which is called MPEG, MP3. MP3 is your music file. So here we are using the MP3. It's the MPEG layer 3. Then for the image part, it uses JPEG, the compression technique. Idea of the JPEG is when you see the image file, a lot of repeated. Okay, when you take the photo, this one, it's almost the same. You don't have to keep each and every information. Instead, something different only. So like this one, we can convert this into the frequency. How much frequently happen this one? Actually 8 by 8 block. Okay, not pixel by 8 by 8 pixel block. How many times repeated? If mostly frequent one, we do not use the full frequency domain. Instead, cut like this one quadrant. Then this one is the most frequent and less. Okay. If we repeat, that is. So this one is the most frequent. We can keep this. Less frequent, we can almost ignore. Okay. Then it's almost 32 times the compression ratio. Huge reduction. Okay. So, however, because of that, the characteristic MPEG and JPEG is you lose some of the information. But good news, human eye cannot recognize the difference. So JPEG is almost you can restore all the data even though it's a high compression technique. So that is based on this. Any such the curve can be represented by combination of sine, cosine, like this. That's also compression, the data reduction technique. I'm going to skip this part. And wavelet is we are going to chop such a signal because the data is not always the infinity periodic graph like that. So we are going to chop the wavelet. The blade means a small thing. So we can make that. Then we can use for the data reduction. Then the PCA. So PCA is another technique to reduce the dimension. So idea of the PCA is here. If we realize B is not important, why don't we remove this feature? Because it's not important, we cannot crash file. We cannot understand the data. A is important. So important the feature we keep, non-important, so primary component. So in terms of PCA, it's called a component. Primary feature. Primary component we keep, and the other feature we throw away. That is the idea, very high level idea of the PCA, principal component analysis. Which one is the important component? Which one is actually the component does not exactly mean the feature. No. So, but I will explain why. But very high level, you can understand that we try to keep the important feature of the primary feature. Then, before I explain this, so I said the feature is different from the component. When we are saying the component in PCA, component means the eigenvalue and eigenvector. Of vector. So anyone who heard about the eigenvalue and eigenvector? I think everyone. Okay, don't be shy. In your math algebra, advanced algebra course, when you learn about the matrix and vector, some of the low-level textbook does not mention directly eigenvector. But you heard about unit vector. Okay, unit vector means the vector space is the magnitude is 1. And this. And for example, Gaussian space like this, the unit vector is u and v. Then this one is called the span. You can represent any vector like the 2, 3 is the 2 u plus 3 times v, like that. Okay? Which is called the span. We can span based on the unit vector. Okay? In case of Gaussian space, it's like this 1, 0 and 0, 1 is the span. So it's the component. It's called eigenvector. So eigenvector means it's the space that span all the value, all the vector in their space. Okay? In other words, important, like the axis, y-axis and the x-axis. Like the axis is the most important, the vector that characterize the vector space. That is called the eigenvector. Then eigenvalue is a scalar value that represent. The unit vector eigenvector is the magnitude is 1. So we do not know exactly how much it's spread out. So eigenvalue is a scalar value that characterizes the magnitude of that space. So what that means is, let's take a look at this one. So 1, you learned about transformation. There are different types of transformation, rotation, okay, and also scalar. Okay, you can scale up, and the x side, y side, and so on. Let's consider 1. So 1, 0 is scale to the is 1, 0, and this one is 0, 1. So this 1, 0, 0, 1 is a 2 eigenvector, 2 important unit vector of the Gaussian space, like that. Okay, like this one. But we'd like to transform this space. This the U 1, 0 is going to 3, 0, which means scale stretch out 3 times. Okay, and 0, 1, 1 part is zero one is go to 2, 1, 2, which means so 0, 1 is stretch right hand side the 1 time. It's not 1 time. Anyway, stretch out this and stretch multiple like this. So this space will be changed to the what? Like this space. Okay? Axis is like this. So if there is any the figure is like this one. This will be like this transform. This is a transformation. Okay, then using the matrix, how can you represent this kind of transformation? How? Very simple, using matrix. 3, 0, 1, 2. That's it. So for example, if you have 1, 0, 1, 0 will be 3, 0, 3. 0, 0, 0. So 1, 0 will be 3, 0. And what about the 0, 1? 0, 1. 0, 2. So 1, 2. What about 1, 1? 3 plus 1, 4, 0, 2. So 1, 2, 3, 4, and 1. So this point will be this one, like that. Yes. So this is a transformation. At that time, so this is a new space. Okay. Here, we try to find the something most important, span. Okay. So that makes the span of the entire the point of new space. Okay. In other words, it's not actually, for example, this one, this point 1, 1 is going to here. So it's not actually the relative to the previous one, but there should be something that the vector that is not actually the moved out from the original point, but it's still here. So for example, the 1, 0. 1, 0 is moved to 3, 0, right? Because of this value. 1, 0, 3, 0. And the 2, 0, 6, 0. 2, 0 will be 3, 0. Minus 1, 0. So any value in this line, the shape is changed. The only difference is stretch out. So this is the one vector. Okay? Another one is, let's see, the minus 1, 1. Let's see, minus 1, 1, minus 3, plus 1, 2. So 2, 2. So minus 1, 1 goes to 2, 2. Not this one. Let me calculate. Minus 3, or minus 2, 2. So this point goes to minus 2, 2. What about minus 2, 2? This one goes to minus 6 plus 2, 0, 4. It's a 4, 4. 4, minus 4, 4. So any line here is on the same line. Then the only difference is stretch out. Okay? So we can find the two line, two vector. this one, and this one. Okay, actually the vector is represent this and this. These two is the main, the component that the form beside the new space. At that time, this kind of vector is called the eigenvector. So eigenvector is not, after transformation, actually it's not changing the shape. It's in the same, the vector, but the only difference is the magnitude is changing. Okay? So, because the importance of the eigenvector is that this eigenvector, combining this vector and this vector, you can represent all the value new space. So this is called the eigenvector. Then at the time, eigenvalue means we don't know how much stretch out. So that the how much stretch out the scalar value is called the eigenvalue. So eigenvalue is the most important characteristic of this one. So for example, if eigenvalue is big, which means it's really stretched out. What if data is stretched out, is it important or not important? It's important because it's stretched out, high variance, right? So we can use for classification and so on. If the eigenvalue is small, like this, narrow, like this, which is not important. So when we reduce the feature, when we reduce the dimension, which one will be removed? Such a low eigenvalue. Low eigenvalue component. It's not actually feature, low eigenvalue component because it's low variance. Okay? Then go back to the original one, then we can classify. So this is the idea of the PCA. Let me use. So PCA is used for the data reduction, but not only data reduction, it can be used for, if we reduce the dimension, it's easier to classify or to model and to be used for the classification. So, principal component analysis use the eigenvector of that data. Eigenvector means it's the kind of the fundamental core vector to span the entire data space. Okay? Then definition of the idea of such a principle, the analysis, the PCA is if we can find such the eigenvector, this one is more high spread, so we like to keep. The another component to this one is narrow, so we can only keep this component. So that's the idea of that. So this is an example of how we can transform like this one. So then we still keep the meaning of the data, but it's the transform. Okay, then we can find the eigenvector, then take out the non-important component. Then we go back to the original data. We will see. So how can we calculate the eigenvalue and eigenvector? So eigenvector, definition of the eigenvalue is A is the transformation, okay, data. In this case, the data matrix, and the times x is equal to lambda is the eigenvalue. Then there. So which means intuitively we try to find the scalar value. That is the same as the matrix. Okay, we try to find the eigenvalue that is the same as this one. So how can you find? So to make this one is a scalar, this one is a matrix, we can add the identification, the matrix, then move to the left, then ax minus lambda I is equal to 0. Then the commutative, then this one should be what? This one is 0. Data is not always 0. It can be any value, so this one should be 0. Right? So if you want to make this one is a 0, means what? Determinant should be 0. Then what is the determinant in matrix? For your reminder, so this is a 2 by 2 matrix. What is the inverse of this one? Anyone who remember? Yes.
A, sorry, E minus C.
A at D is still there, minus B, minus C, and
1 over AC minus
this one, right? Then at the time, this one is called determinant. So what if this one is a 0? Doesn't make sense, which means you do not have a solution. Or unlimited solution, because it's a 0. Like in case of the subparallel linear system of equation or overlay. So go back to here. If you want to make this one is 0, which means it's a no solution, which means this one determinant of this one is a 0. How can you calculate this one? Take a look at your textbook. Algebra textbook, there's a way. AD minus BC is a special case for 2 by 2. 3 by 3 you can do that using minor and so on. The 4 by 4 you can do, but nobody do the programming by yourself. Instead you can use the library, math library, to calculate the determinant. Then we can find the value for the lambda. So lambda is the scalar eigenvalue depending on how much strip out. So higher value and lower value. Which one is important? Principle. Higher value means higher barriers, like that, and it can be used for classification and more important. So we try to keep such a higher value principle. That is reason is called the principal component analysis. Then what if after we found the principal component, we had the PC1, PC2, PC3, which means lambda is higher and this lambda is lower. So this one definitely important. This is not important. Then we have only 2 principal components, right? This is originally 3-dimensional data, but once we find all lambda, the eigenvalue, this one is not important. We take out, remove. Then when we go back to the original data, it will be 2-dimensional data with the principal component 1 and 2. Much easier to classify. Okay, that's the idea of the principal component. I skipped a lot of math. You don't have to worry about too much, but it's better to understand. Okay? Then let me use the example for last. The link is posted, so principal component analysis. PC. First, using the whole data set, okay? Then we need the mean vector to calculate the determinant, okay? And either to calculate the variance or the scattered matrix is the same as the variance. After we calculate the eigenvector using the covariance or the scattered, then we can the result by the eigenvalue, and lower eigenvalue will be removed. Then go back to the original the data. So this is the overall process. let's see the example. So in this example, we randomly generate the 20, the 3-dimensional data. 23-dimensional data. Okay, if we plot data, it's like this. It's 3 dimensions. Okay, there are 2 classes. One is the circle, another one is the triangle. So we try to classify this. But the 3 dimension is too high. We try to apply PCA. So after we apply the PCA, lowest lambda value, the eigenvalue, the component will be removed. Okay, so first, calculate the mean value for each the feature, like the first, second, third, the element. Then calculate the variance. So this is a covariance metric. Actually, it's not covariance metric. It's a scattered metric, but it's the same ratio, same scale. So this is a covariance metric. Divided by the number of items, normalized by the number of data. So it's actually basically same thing. You can use either of them. So let's use the covariance metric. Okay. So using the mean and the covariance metric, we can calculate the eigen, the vector, and this is the first eigenvector, and this is the second eigenvector. Meaning is these are the 3, because it's a 3-dimensional data. We have 3 eigenvector. These the eigenvector span the entire space without changing the form. It's still the existing, still the same the line, but the only difference is the scalar. So we can calculate the scalar value. Here's a scalar, not scalar value, yes. So using the new vector, this is the eigenvector. Okay, this vector is not changing the direction, only scalar will be, magnitude is changing, new one. So from here, we try to calculate the scalar is the component 1, component 2, component 3, which means this one is the eigenvalue, meaning is non-important. It's the narrow. So we take out this third component from the eigenvector, then transform into the original one. Then if we plot, because we remove the third one, it will be 2-dimensional data. It will be plot like that. Then after we got this one, we can cut like this, because the left-hand side is more the triangle, right-hand side is this. Or you can apply the linear regression over here. Okay. So this is the overall process of the PCA. So key part of the PCA is you should be able to calculate the eigenvalue, then eigenvector. That's it. So to do that, you definitely understand what is the eigenvector and eigenvalue. So eigenvector is kind of characteristic of the new space. So it doesn't change the direction, but it has only changed by the magnitude, that is the eigenvalue, scalar value. Okay. So using that scalar value, we decide which one is important, which one is primary, which one is not. Then after we take out that dimension, go back to the original one. Okay. So this is the PCA. This PCA will be used for not only the dimension reduction, but it can be used for classification problem. So next time, I'd like to introduce the one more, the dimensional reduction, that is the regression. Then briefly introduce. Later we will see the more detail, but briefly see how can we use the PCA and regression for the classification problem. It's a machine learning problem, so which is called the generative and discriminative learning, like that. Okay, so because the class lecture is not enough to understand everything. So you have homework, exercise lab. Where is it? The programming assignment. Let's see here. Yes. So the first programming assignment is implementation. of the PCA. To do that, first definitely you need to understand the PCA. So using class note or the other internet source, first you need to understand that, implement. So when you implement, I know, scikit-learn, the PyTorch, math, a lot of the existing PCA library. Do not use existing PCA library, okay? It's just a one-line code. There's no the benefit to use. Later, after you understand, it's okay, but this homework, with your own code, implement the PCA. Even it's a 10, 12 line, maybe enough. You don't have to fully implement like that. If you are using the Python, you can use a NumPy, okay, array. Otherwise, you can use a two-dimensional array in terms of Java tuple. Another thing is you can recycle existing code. But I'm not going to allow to use the library, okay, PCA library. So instead, you can find any existing code and recycle it. But at this time, you can find the 3 data set from the UCI. You can, if you go to the UCI data set, it's the most popular data, machine learning and data mining, the repository. Find decide the 3 data set and apply to your code, PCA code, and see the result. Okay? Then at that time, definitely the UCI data set, their data format, not feasible to your code sometimes. So you can manipulate. So can use that. Okay. Visualization is an extra point. So you can do the after transform data set and visualize them. Like the previous example. You can find the link from the lecture note. This data set will be used for the next second programming assignment is a neural network and naive Bayesian later. Okay, so this one is due by 2 weeks later. Okay, so you have a time, but so please start your homework. Then next class we will complete the regression model very quickly. Then move to the association rule mining quickly. And also, if I receive all the item, I will hand out the second project the material. Any question? We did a lot of things this week and last week, but these are very important to understand. And also, one more time, if you are interested to submit the poster later, it's just an abstract, half-page abstract. So why don't you discuss? You don't have to have the result or anything. Just the abstract is okay. If your abstract is accepted, I will give the 15% extra credit for the finance. Okay, for the finance, it's huge. It's a please try, and it's a good experience. Anyone who did participate in the last year AC Niagara?
Last
So,
year.
yeah, so it's a very useful for you guys, and you can fill out your resume and your LinkedIn like that. Okay. Thank you so much. We will see you next week.